Mhm. Am I audible? Am I audible? Good evening, everyone. Welcome to Goscore Learning, the fastest growing edtech company in Middle East, and our main aim is to provide quality education for all. I am your Dhanya ma'am with the second part of your electrochemistry chapter. In the first part of electrochemistry, we have discussed regarding the electrochemical cell, galvanic cell, and how we can represent the cell. I think all that portions are clear for everyone. Today, we are going to discuss about the electrode potential, standard electrode potential, EMF of a cell, and the Nernst equation. So, can we start the session? First, we can discuss about the electrode potential. Okay, so what is an electrode potential? The electrode potential is the potential difference that's set up between a metal when it is kept in its own solution. If you are keeping a metal rod in its own metal solution, then there will be a potential difference, and that difference is called a electrode potential. Okay, I will explain it in detail. See, here we have taken three beakers. Okay, I'm taking three beakers. Okay, in each beaker, we are taking a salt solution of a metal M. Okay, we are representing the metal with M, and we are putting the metal rod M in the solution. We are putting the metal M. We are putting the metal M, and this is the salt solution of that metal. This is the salt solution. Okay. Same way, I'm taking it in the remaining three beakers also. Okay. Just I will draw, then we can explain it in detail. Okay. We are putting the metal rod, M, and we are filling the beaker with the salt solution of the same metal that we dipped in that beaker. Okay. So this is the metal M. Okay. So now I'm going to explain what will happen. There are three possible chances. Okay. When you dip the metal rod in the metal solution, three possibilities are there. That means here we know that in the salt solution definitely there will be another ring. Definitely there will be what? Mn plus ions. The metal ions will be there, right? So in the salt solution there will be in the salt solution there will be metal ions that I am representing with the Mn plus. Okay, here also. Okay, this is the metal, right? So I told you there are three possibilities. The first case is that where this Mn plus ions, the metal ions, will hit this metal and deflect back, and no reactions taking place. Okay, there no changes are happening. This metal ions hit the metal surface and reflect back without any change. That is the first possibility. In the second case, what happens is this metal ions will accept n electrons from the metal and convert to metal M. Okay, this metal ions will accept n electrons. Yes, last session we have discussed the electrons will never be on the solution. It will always be on the metal rod, right? So it will get the electrons from the metal rod and convert it to M. Okay, that is the second case where what we can see, this metal ions are accepting the electrons. Accepting the electrons means these metal ions are undergoing reduction process, right? So in this case, in the second case, the metal ions are reduced to M metals. Okay. Then what will be the third case? In the third case, this metal will be converting into metal ion by losing N electrons. Okay. So here in the third case, the metal will be losing n number of electrons and convert to metal ions. Their losing of electron, that means the metal is getting oxidized, right? Okay, here the metal rod is getting oxidized to metal ions. So in all these cases except this first case, see here from the solution the ions are converting to M. Here from the metal rod the M is converting into metal ions. So definitely there will be a potential difference, right? So that potential difference is called the electrode potential, or simply we can say the tendency of a metal to lose or gain electron when it is kept in its own solution. Okay, see the tendency of an electrode, the tendency of a metal electrode to lose or gain electron when it is in contact with the solution of its own ion, or when you kept the metal rod in its own salt solution. Okay, that is that potential difference, that setup is called the electrode potential. Electrode potential difference set up between the metal and the metal ions. Okay, the metal ions present in the solution is called the electrode potential. Now you understood why that potential difference is coming when you keep it there. Either the metal ions will accept the electrons and the metal ion will undergo the reduction, or the metal will lose the electron. That means the metal will undergo oxidation. So that creates a differences in the potential. Okay. So okay, we have kept the metal rod in the its own salt solution and we got the electrode potential. We understood why it is the electrode potential. If you are keeping the metal rod in a 1 molar solution of its salt solution, okay, you are keeping the metal rod in a 1 molar concentration of the salt solution at 298 Kelvin. Okay. In a cell, if the metal rod is suspended in a solution of 1 molar concentration at 298 Kelvin, then their electrode potential is called the standard electrode potential. Okay, so standard electrode potential is the electrode potential of an electrode which we have kept in the 1 molar concentration. 1 molar concentration of the metal salt solution at 298 Kelvin. Okay. So I hope the standard electrode potential is clear for you. In a half cell, we have learned the cell in that electrode, 2 electrodes, cathode and anode is there. So if you are keeping the cathode or anode, whatever it is, it will be oxidation potential and reduction potential. If you are keeping the electrode in 1 molar concentration of its salt solution at 298 Kelvin. Okay, the temperature is very important and the concentration is 1 molar concentration. Then the electrode potential is called the standard electrode potential. We will usually represent the electrode potential with a letter, capital letter E, and if it is standard electrode potential, we will represent it with E naught. Okay, that's what the representation of standard electrode potential. Okay, so there we have learned the metal can act as a standard oxidation potential will be there. Reduction potential can happen. It all depends on what type of the solution we have kept, and in a cell whether we have kept it as the cathode or as the anode. Okay, not kept, it act as a cathode or as a anode. Okay, now see the measurement of electrode potential. So how can we measure the electrode potential of a metal? If you want to find out the electrode potential of a metal, we cannot do it by single, because we should have a half oxidation half reaction and a reduction half reaction. Then only we can find out the electrode potential, right? So in order to measure the electrode potential, we have to use a reference electrode. If you want to find out the electrode potential of a particular metal or particular metal electrode, you have to compare the electrode potential with a reference electrode. And that reference electrode is called the standard hydrogen electrode. Okay, we will be using the reference electrode, standard hydrogen electrode, which is SHE. Okay, She. We will be using this standard hydrogen electrode as the reference electrode for measuring the electrode potential of any particular metal electrode. Okay, now see what is the standard hydrogen electrode. How we can find out the electrode potential using this sheet. Okay, so in the standard hydrogen electrode, I will draw the picture and I will explain it. Okay, so and this is the standard hydrogen electrode. Here we will take the 1 molar HCl solution. Okay. So in a standard hydrogen electrode, we will be taking the 1 molar. This is the 1 molar HCl solution. Okay. To this 1 molar HCl solution, we will be passing the hydrogen gas through this inlet. We will be passing the hydrogen gas at 1 atmospheric pressure. Okay. To this 1 molar HCl, we are passing the hydrogen gas at 1 atm. Okay. And also, there will be a connecting wire. Okay. This is the connecting wire and it has the platinum black at its end coated with some it has a platinum end coated with some platinum black. Okay, now see, this will be the connecting wire. This is the platinum. Okay, so this is what the diagrammatic representation of a standard hydrogen electrode. It will contain the hydrogen gas at a 1 bar pressure. 1 bar pressure, we will be applying the hydrogen gas, and to the where we have taken the 1 molar HCl and the temperature should be 298 Kelvin. We are maintaining the temperature at 298 Kelvin, in which in this 1 molar HCl to 298 Kelvin, there will be a platinum coated with a platinum bag is immersed. This platinum will act as an inert electrode It will act as an inert electrolyte and thereby help in the inflow and the outflow of electrons. Okay, that is the role of the platinum. This is what the setup of a standard hydrogen electrode. The standard hydrogen electrode can act as both as an anode as well as a cathode. Okay, see what happens if it acting as an anode. Here we are passing the hydrogen gas, right? So at the anode, what happens? At anode, oxidation will happen, right? Oxidation means losing of electron. So at anode, this hydrogen will be converting into 2H plus 2 electron. And at cathode what happens? The reduction reaction, right? Reduction means gaining of electron, where the 2H plus ions is from this HCl. From this 1 molar HCl, the 2H plus ions will be accepting 2 electrons and converting into H2 gas. See, if this standard hydrogen electrode act as an anode in a cell, what will happen if it is acting as the anode? The hydrogen gas that we passed through this inlet will be converting into hydrogen ions, okay, and entering into the solution. If this standard hydrogen electrode we are keeping as a cathode, then reduction will occur at the cathode and the H plus ions from this 1 molar HCl will accept 2 electrons and converting to H2 gas. Okay, so what we understood from this, the standard hydrogen electrode can act both as cathode as well as the anode. Okay, and the standard electrode potential. The very important thing is that the standard electrode potential of standard hydrogen electrode will always be taken as 0. Okay, now let's see how we can measure the electrode potential. The difference between the electrode potential of the two half cells is called the cell potential, and it is also called the electromotive force or EMF of the cell if no current is drawn from the cell. So the EMF of the cell is the sum of oxidation potential and the reduction potential. We will explain the EMF of the cell in detail after discussing the electrochemical series. Okay. And here we have taken in the cell, we have taken the one electrode as the standard hydrogen electrode, and the next electrode is the metal whose electrode potential that we want to find out, that we want to investigate, right? So how we will investigate? We will keep that metal electrode as the anode or cathode, and it will be connecting to the standard hydrogen electrode to form a cell. Okay, and I told you the electrode potential of the standard hydrogen electrode is always taken as 0. Okay, so once the one of the electrode in the cell is standard hydrogen electrode and its electrode potential is always taken as 0 value. Okay, so the potential difference in the cell, that is the EMF. Okay, the EMF, the potential difference in the cell is directly give the electrode potential of the electrode in which that what we want to investigate, or the electrode potential of the metal that what we want to find out or to measure, right? So that is how the standard hydrogen electrode help us to measure electrode potential. Understood? We will connect the standard hydrogen electrode with the metal rod that we want to find out the electrode potential. Okay, then once the cell is connected, we will get the voltmeter reading, and from that we can find out the electrode potential of the metal to be investigated by taking the electrode potential of standard hydrogen electrode as 0 value. Okay, and the direction of flow of current will indicate whether oxidation or reduction takes place at the electrode with respect to standard hydrogen electrode. The flow of the electron will give you the idea whether at the metal electrode oxidation is taking place or reduction is taking place with respect to the standard hydrogen electrode. You will get this concept clear by explaining the example, that is, we are going to find out the standard electrode potential of zinc electrode. Okay, here we want to find out the electrode potential of zinc electrode. So what we will do, we will take the 1/2 cell as the zinc metal dipped in its salt solution. We will take the zinc sulfate solution and we will dip the zinc metal, that is our 1/2 cell. The second half cell will be the standard hydrogen electrode. Okay, let's see how we will connect it. See, here we want to find out the electrode potential of the zinc, right? So I'm taking the salt solution of zinc, that is the zinc sulfate. Here I'm taking zinc sulfate, to which I'm dipping the zinc metal. Okay, I dip the zinc metal in it. The next side, what we will take, in order to find the electrode potential of a metal, we should need a reference electrode, and the reference electrode is standard hydrogen electrode, right? Here we are taking the standard hydrogen electrode. We know that in the standard hydrogen electrode, what we will take? 1 molar HCl solution, right? This is the 1 molar HCl solution, and the same one we draw for the standard hydrogen electrode. There will be an inlet for the entry of hydrogen gas, okay, through which the hydrogen gas, okay, hydrogen gas at a 1 bar pressure will be coming. Okay, the hydrogen gas at a 1 bar pressure, and there will be connecting wire. There will be a connecting wire with a platinum ending it. Okay, so, and we know that in a cell we have to connect the two cells using the salt bridge. Why we are using the salt bridge, the importance of salt bridge, everything we have discussed in the first part. Okay, so we are connecting the two half cells using the salt bridge, and of course there will be a galvanometer, and when you connect this, we can see that here what will happen, the zinc will be converting to Zn2++ to electrons, right? So the electron flow will be from here to here, the flow of electrons. Okay, so once you connected this, what we will understood, the electron, the zinc is donating the electron, that means it is undergoing oxidation. So in this one, the zinc will act as the anode, and here the standard hydrogen electrode will act as the cathode. And once you connected, what the value you are getting, the reading you are getting will indicate the electrode potential of the zinc electrode, right? Because I told you the standard hydrogen electrode, the electrode potential will be taken as 0, and whatever the reading you are getting will be the electrode potential of the zinc metal. Okay, and the oxidation potential of the zinc, oxidation potential of zinc was found to be 0.76 volt. Okay, the same way we can find for the copper also. So for determining the electrode potential of copper electrode, what we have to do? We have to take the copper metal and dip in the copper sulfate solution. That will be your half cell. Same way, we will be taking the standard hydrogen electrode as the second half cell, connecting the two half cells via with the salt bridge, and with the reading and the flow of the electron will indicate which one is acting as the cathode and which one acting as the anode. Let's see how we can determine the standard electrode potential of copper. So for copper, this will be copper sulfate solution we are taking, and we will dip the copper metal in it. Okay, we will dip the copper metal in it. The next second half cell will be, of course, the standard hydrogen electrode. In that, what the liquid is 1 molar HCl, right? We're passing the hydrogen gas. The connecting wire with the platinum, inert platinum at its end. Okay, it will help to for the inflow and outflow of the electrons, right? Yeah, we're connecting the. Okay, this is the galvanometer. And when you connected it, you can see the electron flow will be from standard hydrogen electrode to copper sulfate. So here Cu2 plus ions are accepting two electrons and converting to copper. That means the copper ions are getting reduced. Reduction. That means they act as the cathode. This will act as the anode. See, for the determination of electrode potential of zinc, the standard hydrogen electrode act as the cathode, and for the determination of copper, it acting as the anode. Okay. Here also, its electrode potential will be 0, and its electrode potential value, that galvanometer reading will show the electrode potential of the copper electrode. Okay. This is how we are measuring the electrode potential of a metal electrode using the reference electrode standard hydrogen electrode. Okay. So now see the next term, that is the electrochemical series. So by using the standard hydrogen electrodes, we have find out the electrode potentials of different metals, right? And we have arranged this electrodes in the increasing values of their reduction potential. And that series is called the electrochemical series. The various electrodes have been arranged in the order of their increasing value of the standard reduction potential, and this arrangement is called the electrochemical series. Okay, now let's see what are the applications of this electrochemical series. The first application is we can compare the relative oxidizing and reducing power using the electrochemical series because it's order arrangement, right? So of course we can compare the relative oxidizing and reducing power. The second thing is compare the relative activities of metals. We have learned from the lower grades that the displacement reaction, right? What is displacement reaction? In which a highly reactive metal will displace the less reactive metal from its salt solution, right? Same way, here, greater the oxidation potential of a metal, if a metal have a greater oxidation potential, it means that it have a greater tendency to lose electron. Oxidation means losing electron. If it have a greater oxidation potential, it means it will have a greater tendency to lose the electron, right? If it have a greater tendency to lose the electron, that means it is more reactive, right? So greater the oxidation potential of a metal, more easily it can lose the electrons. That means it is more reactive. And Same like displacement reaction, the metal with a greater oxidation potential, that means it is more reactive, right? It can displace a metal with less oxidation number from their salt solution. Okay? The metal with a greater oxidation potential can displace the metal with lower oxidation potential from their salt solution. Okay, so the oxidation potential of magnesium, zinc, iron, copper and silver, it will follow the order. The magnesium having the greatest oxidation number, then zinc, then iron, then copper, last silver. Okay, so this is the oxidation order, oxidation potential order. Definitely, that will be the reactivity order. We know that magnesium is more reactive than copper, silver. Okay, so that is what we can compare the relative activities of a metal. If the metal is having a greater oxidation potential, it will have a greater tendency to lose the electrons. That means it will be more reactive. That is the second application of electrochemical series. Now see the third application. So for a spontaneous reaction, we can predict the spontaneity of the redox reaction by using the electrochemical series. That is, for a redox reaction to be spontaneous, the EMF of the cell must be positive value. Okay, the EMF of the cell must be positive value for a spontaneous reaction. So if you are getting a EMF positive, that means the reaction is spontaneous. So that way we can predict the spontaneity of redox reactions. And the last application is the calculate the standard EMF of any galvanic cell. We know that in galvanic cell there will be an oxidation half cell and a reduction half cell, right? Okay. So, what will be the EMF of the galvanic cell? The EMF, that is the electromotive force, is equal to, it is the sum of the standard oxidation potential plus standard reduction potential. The standard oxidation potential of electrode where oxidation taking place, oxidation half reaction occur, plus standard reduction potential of the electrode where reduction half cell or the reduction half reaction is taking place. So we can write the EMF is equal to standard electrode potential of oxidation half cell. Standard oxidation electrode potential of oxidation half cell of the galvanic cell plus standard reduction, not standard oxidation, standard oxidation potential. Standard oxidation potential of oxidation half cell plus standard reduction potential of electrode where reduction half cell reaction is carrying out. Okay. Okay. And I forgot to mention one thing, that if you get the standard oxidation potential, the standard reduction value of that particular electrode will be simply the negative sign. Okay. If you are getting, we got the standard oxidation potential. Standard oxidation potential of zinc electrode Zn bar Zn2 plus as 0.76 volt, right? Then its standard reduction potential value will be simply the negative value. Okay. Then the standard reduction potential of zinc electrode will be minus 0.76 volt. Okay. So here what we can write, the oxidation is occurring at the anode, right? Reduction potential is the reduction means it will be taking place at the cathode. isn't it? So this is the standard oxidation potential of the oxidation half cell, right? That I can write it as the negative sign of the standard reduction potential of that same half cell. Okay, so I'm rewriting it like minus of reduction, sorry, standard reduction potential of the particular electrodes half cell plus the same thing, the standard reduction potential of reduction half cell. So this is the E cell, EMF of the cell, electrode potential of cell. This is the standard potential of anode, right? So minus E naught standard electrode potential of anode plus E naught. This is for the cathode, right? So what we can write, the standard electrode potential of cell is equal to the standard electrode potential of cathode minus E naught anode. Okay. So E naught cell is equal to E naught cathode minus E naught anode. Okay. This is the This is how we can find out the standard EMF of any galvanic cell using the electrochemical series. So with this equation, let's see one numerical. Here, calculate the standard EMF of a cell which involves the reaction Zn plus 2Ag plus giving Zn2 plus 2Ag. That is zinc plus silver ions, zinc ion plus Ag. Okay, so given that the standard electrode potential, it is given the standard oxidation potential, the standard oxidation potential of zinc is 0.76 volt and the standard oxidation potential of silver is minus 0.80 volt. So how we will find out the EMF? The EMF is equal to negative of the reduction potential of the anode plus reduction potential of cathode, right? Here we have provided with the oxidation potential value. So what we will take, which one will act as the cathode, which one will act as the anode? See, zinc is converting into Zn2 plus 2 electrons, right? It is losing the electron, that means it is undergoing oxidation and will act as the anode, right? And for silver, 2Ag plus will be accepting 2 electrons and converting into 2Ag. That means reduction process occur and it will act as the cathode. But here the oxidation potential values are given. Either you can convert one into negative value and you can add the oxidation half cell plus reduction half cell, or you can convert the both into opposite sign and can use the formula E naught cathode minus E naught anode. Okay, so here silver will be acting as the cathode, but its oxidation potential value is given. So I am taking it as the, it is negative 0.80 is the oxidation potential. So positive 0.80 will be the reduction potential, right? Minus the oxidation potential of the anode is given 0.76. If you are converting into reduction potential of the anode half cell, it will be the negative sign. Then it will be minus of minus 0.76, right? So what you will get? 0.80 plus 0.76. That will be 1.56 volt will be your answer. Okay. Here, if you get a questions like this, first you have to find out which one will act as the anode, which one will act as the cathode, and look at the question whether the oxidation potential or reduction potential is provided, and based on that you have to take the negative sign values. This problem you can take as this one you can take as the cathode, you can take as the oxidation half cell plus the reduction half cell. There you have to take the negative value, then also you will get the same answer. Okay. So if you get the concept, you can solve the problem based on any three equation. Here we have learned three ways, right? Either you can use this one or you can use this one to get the answer. In any way, you will get the same answer. Okay. Now go for the next question. A cell prepared by dipping a copper rod in 1 molar copper sulfate solution and a nickel rod in 1 molar nickel sulfate solution. The standard reduction potential of copper electrode and nickel electrode is 0.34 volt and minus 0.25 volt respectively. You want to find out the cell reaction, standard EMF of the cell, which electrode will be positive, and how will the cell be represented. Okay, so here they have given the standard reduction potential directly. So no need to change the sign of the potential. You can use the E naught cell is equal to E naught cathode minus E naught anode directly to this using this values and it is a cell prepared by dipping copper in copper sulfate, that is 1 molar copper sulfate solution and a 1 molar nickel in 1 molar nickel sulfate solution. So there, what will be the cell reaction? There can be two possibilities, right? But what we learned for a spontaneous reaction, the EMF of the cell must always be positive value, right? So let me check which value you will get the positive one. That will be the cell reaction. Here, nickel plus copper sulfate gives NiSO4 plus copper, or copper plus NiSO4 will give two possibilities are there, right? The case 1 and case 2. Let me check the case 1. If you are getting the positive value, no need to check for the second case, right? So in the first case, what is happening there? Nickel plus copper sulfate, it will contain Cu2 plus ions, right? We'll be giving Ni2 plus C. Here, the nickel will be converting into Ni2 plus nickel ion plus 2 electron. That means it is losing the electron, it is undergoing the oxidation and it will act as the anode, right? And then copper Cu2 plus 2 electron converting into copper. That means it is accepting the electron reduction and it will act as the cathode, right? Now let's check the electrode. Standard electrode potential values are given. Then E naught cell will be equal to E naught cathode minus E naught anode, right? So what the values you got here? E naught cell is equal to E naught cathode minus E naught anode. Cathode is copper and the copper electrode and nickel electrode. Copper value is 0.34, right? 0.34 minus 0.25. So E naught cell is equal to 0.35 minus this value is 0.34 for cathode minus what is the value for the anode standard electrode reduction potential of anode? It is minus 0.25, right? So it will be minus 0.25. That means 0.35 plus 0.25. 0.34. 34 plus value given is 0.34, right? So it will be 0.34 plus sorry 0.25. Okay, so what will be your standard electrode potential value? It will be 0.59 and you are getting a positive value, right? That means the possible cell reaction is this one. Okay, so the possible cell, what will be the cell reaction? It will be nickel plus Cu2 plus gives Ni2 plus copper. Okay, and now you got the second answer also. What will be the standard EMF of the cell? What the value you got? The standard EMF of the cell will be 0.59 volt, right? So the standard EMF of the cell will be 0.59 volt. And which electrode will be positive? Here, see, at the anode, the nickel is losing 2 electron, right? So there will be a electron cloud and this will be the negative pole, right? And from in copper electrode, what happens? It is accepting the electron, right? So which electrode will be positive? Definitely the copper electrode will be positive, right? And how will represent the cell? Representation of cells already we learned in the first part of this electrochemistry chapter. First we will write the anode, then we will write the put two lines to sorry, we will put two lines to represent the salt bridge, then the cathode. So here which one is the anode? So Ni slash nickel ions. Okay, and either you can write NiSO4 or Ni2 plus ions, and the concentration is mentioned in the question, that is 1 molar concentration. So you have to mention the concentration and represent the salt bridge with two lines, then write the cathode. Cathode is Cu2 plus ions copper, and the copper ions concentrate, copper sulfate concentration is mentioned as the 1 molar. So this is the way we will represent the cell, the anode, then the salt bridge, then the cathode. Okay, so I hope this question is clear for you. Now let's see the next important thing, that is the Nernst equation for an electrode potential. So till now we have discussed that how we will find out the electrode potential of a metal electrode if we kept it in the 1 molar solution, right? So if we are not keeping in the 1 molar concentration, we are keeping it in a concentration other than the 1 molar concentration, how we can find out the electrode potential? So therefore, finding out the electrode potential, we are using the Nernst equation. See, what is Nernst equation? How we can apply that for finding out the electrode potential of a metal electrode, as well as we want to learn the cell also. Okay. So, metal Nernst equation for a metal electrode. We can consider the metal Mn plus metal. N plus means it is losing n electrons. Okay. So same way what we are writing Zn2 plus, that means zinc is losing 2 electrons and converting to zinc ions. Same way we are taking the metal M, and if it is losing n electrons, that is what is represented by Mn plus. Okay, Mn plus accepting n electrons, it will be converting into M, right? So here we are not keeping the metal electrode at the 1 molar concentration, then how we can find out the electrode potential? Okay, here the temperature will be 298 Kelvin. Okay, so for this, the electrode potential is E, electrode potential of the, not we are mentioning for the metal electrode, right? Not for the cell. So E will be equal to electrode potential of the metal electrode will be equal to standard electrode potential E naught minus R T by N F natural log concentration of the metal divided by the concentration of the metal ion. So it will be Ln concentration of metal divided by Mn plus. Okay, and it's clear that for pure solids and liquid substances, the concentration will be taking as unity. So here the concentration of metal will be equal to unity, that is 1, right? And what is this E naught? It is the standard electrode potential of the metal electrode. And what is this R value? We know that the R value is, what's the R value? It is 8.314 joule per Kelvin mole, right? And what is this temperature? I told you we are just changing the concentration only, but the temperature will be 298 Kelvin. Okay, it can be 253, 25 degrees Celsius or 298 Kelvin. Both are same, right? And F is Faraday's. And what does this N indicate? N is the number of electrons that participated in the redox reaction. Okay, N represent the number of electrons, and this is the natural law. This is the concentration of metal and metal ions. Okay, so we know the values of this gas constant, temperature, Faraday. When we are converting the Faraday into Coulomb, we will take it as the 96,500 Coulomb. Okay, so once we substituted these values, what the equation will be. So before that, we can convert this natural log into log. That will be E naught minus RT by NF. How we will convert the natural log to log? By multiplying with the 2.303. 2.303 log M. Already I told you this M value we will take as 1. So what we can write? 1 by concentration of metal ions, right? So after substituting the values of R, T and Faraday, what we will get is electrode potential of the metal electrode at concentration other than 1 molar concentration is equal to standard electrode potential of that metal minus 0.059 divided by the number of electrons into log 1 by concentration of the metal electrode. Sorry, metal ions. Okay. So, this is the equation for finding out the electrode potential of the metal which we kept in the concentration other than 1 molar concentration 298 Kelvin. Okay. So, now let's see one numerical based on that equation. So, the equation is E is equal to E naught minus 0.59 divided by N log 1 by concentration of the metal ion, right? So, calculate the electrode potential of copper wire dipped in 0.1 molar copper sulfate solution at 25 degrees Celsius, and the standard electrode potential of copper is 0.34 volt. Okay. So, here the concentration given is 0.1 molar. Okay. Now see how we will find out the what we want to find out. the electrode potential of copper wire and its standard electrode potential, that is E naught value is given in the question, right? So Cu2 plus 2 electron giving copper. Okay, and the electrode potential of copper is equal to E naught minus 0.059 divided by N log 1 by concentration of Cu2 plus ions, right? And the E naught value, it is given 0.34 minus 0.059 divided by how many electrons are involved here? 2 electrons, right? So N value will be 2 log 1 by, what is the concentration of copper sulfate? It is 0.1. Okay, that I can write it as 1 into 10 raised to minus 1, right? So what will be the value? 0.34 minus, this will be 0.0295, right? 0.0295. What will be log 1 by log 1 into 10 raised to minus 1? Log 1 minus 1 into log 1, right? So it will be log 1 0 minus of minus 1 plus 1. Okay. So your value will be 1 there. So you want to find out 0.34 minus 0.0295 will give you the electrode potential of the cell. That means 0.34, right? Okay. So your answer will be 0.31 volt will be the electrode potential of copper electrode. Okay. So this is the way we can simply, if you know the Nernst equation for the metal electrode and if you understood the question, you can easily get the marks by applying the equation and substituting values. Okay. Now let's see the Nernst equation for the EMF of the cell. We have discussed how we will find out the electrode potential of a particular electrode using the Nernst equation. Now let's see how we can find out the Nernst equation for the EMF of a cell. Okay, so for that we are considering the galvanic cell. In that the zinc plus Cu2 plus ions is giving Zn2 plus and copper. Here we know that the zinc will be the undergoing the oxidation. It acts as the anode and the copper will be the cathode, right? So for that, how we can write the equation? E naught cell will be equal to E naught cathode minus E naught anode, or what we can write, E cell is equal to E cathode minus E anode, right? Then what is E cathode? Cathode is copper, right? So what is E cathode? How we can find the electrode potential of copper using the Nernst equation? What we learn now, it will be equal to, it's for copper, Cu2 plus slash. So it will be equal to E naught copper minus RT by, and here it is 2, right? 2F ln 1 by concentration of Cu2 plus, right? Then what about the anode, that is Zn bar, Zn2 plus will be E naught Zn2 plus Zn minus RT by 2F ln 1 by concentration of Zn2 plus, right? So What do you want to find out? The subtract these values, right? So it will be E cell is equal to E naught cathode, that is E naught Cu2 plus slash copper minus RT by NF ln 1 by Cu2 plus minus 1 by Zn2 plus concentration, right? So after rewriting equation, what we will get? E naught Cu2 plus dash Cu minus, this is minus of, right? So it will be E naught Zn2 plus slash Zn minus, what is common in this two? RT by NF, right? RT by NF, you will get ln Zn02 plus divided by this value, right? So it will be Zn2 plus dash Cu2 plus value you are getting. Okay, so what is this one? E naught cathode minus E naught anode, that is the E naught cell, right? E naught cell minus, if you substitute the values of RT and converting it into log value, what we will get? 0.059 divided by N log concentration of Zn2 plus by CO2 plus. So what it comes on the right hand side will be on the numerator, and what comes on the left hand side, the ion coming on the left hand side will be in the denominator. So that is the E cell. Okay, this is how we are finding out the EMF of the cell, electrode potential of the cell, using the Nernst equation, and it is E cell is equal to E naught cell minus 0.59 divided by N, where N is the number of electrons, into log concentration of Zn2 plus divided by Cu2 plus. Here, for a general equation, for a general equation, AA plus BB giving CC plus DD, we can write the E cell as E cell is equal to E naught cell, the standard electrode potential of cell, minus 0.059 divided by N, 0.059 divided by N log product. Concentration of C raised to stoichiometric coefficient C, D raised to stoichiometric coefficient D, divided by reactant. A raised to A and B raised to B. This is for the general equation, how we can represent EMF of the cell. Okay. So now see one question based on this question. Represent the cell in which the following reaction takes place. Mg plus 2Ag plus concentration is given 0.0001 molar, giving to Mg2 plus with concentration 0.130 plus 2Ag. And you have to calculate the E cell, and the values is given that E naught values is of magnesium, and standard electrode potential of silver, it is given in the question as minus 2.37 volt and 0.80 volt respectively. So what you want to find out, we have to substitute the values, as you will get the answer, right? So the equation will be E cell is equal to E naught cell minus 0.059 divided by N log, here the concentration of product will be Mg2 plus divided by, see here what you have to check, Ag plus with the stoichiometric coefficient 2 is there. So how we will take? It will be Ag plus raised to power 2. So don't forget to take the stoichiometric coefficient there. Okay. So now it's all simple. It's E0 value, E0 value. It is given from this. The magnesium is changing to Mg2 plus 2 electrons. Since it is losing the electron, it will act as the oxidation and it will be undergoing oxidation and act as the anode, and 2Ag plus 2 electron. 2 silver is forming. It is accepting the electron. That means it's undergoing reduction and will act as the cathode, right? So here E0 cell is the E0 cathode minus E0 anode, right? So which one is the cathode? Silver. So this will be the value 0.80 minus 2.37. So what you will get here, 0.80 plus 2.37, that will be your E0 cell value. Okay, that means 3.17 volt will be the E0 cell value minus 0.59 divided 0.059 divided by what is the number of electrons here? How many electrons are there? 2 electrons, right? So it will be 2 log, what is the concentration of Mg2 plus? It is 0.130 divided by concentration of silver ions is 0.0001, that I can write as 10 the power minus 4 raised to 2, right? So what will be your value? It will be 3.17 minus 0.029 into log. This will be 10 the power minus 8. If you are taking on the numerator, 10 the power 8, that I can write as 1.3 into 10 raised to 7, right? So by doing the calculation, you will get the value as 2.96 volt as your answer. Try to solve the question and let me check if you are getting the answer correctly. Okay, so I hope the session, the Nernst equation, how we are finding out the EMF, what is the electrode potential, what is the role of standard hydrogen electrode, and how we can find out the electrode potential other than 1 molar concentration by using the Nernst equation, and the same one how we can find out for the EMF of the cell using the Nernst equation. This portion is clear for you. I will be coming with the third part of this electrochemistry chapter soon. Until then, stay tuned with Goscore Learning Center. And also one more thing, your Nandini ma'am will be coming on live on Tuesday with physics class. Okay, thank you.